Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with assignment Class 6, a taste of model selection for multiple regression using a PSA, prostate-specific antigen dataset that will bring in several additional skills compared to Class 5. So we'll go down to Class 6 and save the RMD file and the data file to our ADA folder. I'll open this HTML for reference in a moment in a new tab, and I will start our studio, open up the markdown file, and knit it. I'll also set the working directory to the source file location. All right, let's go review the beginning of this assignment. All right, so PSA, the prostate-specific antigen, is a measure that has long been used for assessing whether an aging male has prostate cancer. And a University Medical Center urology group wanted to know what the association was between PSA and a few other measurements in men with advanced prostate cancer. We've got a data set of 97 men who are about to undergo a radical prostatectomy. So when we start to think about whom this analysis will infer to, it has to infer to a group of people like what's in the sample. So these are all men with advanced prostate cancer who are about to undergo radical prostatectomies. So these men are probably fairly far along, and also men who are actually going to get their prostate removed. So this group of men is different than the global population of men. So these relationships may not hold more generally over all men. So that's sort of something to be thinking about for the very last question. This data set has more variables than we're using. We're using the ones with the star next to them. We've got the PSA level. We have the cancer volume, the prostate weight, and the man's year, or age in years. Please read this background to sort of get some background about what we're looking at. The rubric here is similar to assignment 5, to build a multiple regression model to predict PSA from those other three variables: the volume, the weight, and the age. And this strategy is the same as what was in Chapter 5, or Class 5. Examine the relationship between the variables, decide whether we need transformations, see what other features we see in the data set, then fit a model, use backward selection to reduce the model to the vital few variables that help predict PSA. Make sure that models fit the model assumptions throughout, and check for influential cases. And we may need to iterate a couple times if we do transformations or remove influential observations. And finally, we'll interpret the model and discuss any limitations we have. All right, so we start by, so the first part is to describe the patterns we see in the data, and so on. So read the data set in. I'm going to scroll down to the, I do rename the variables. I probably wouldn't do this for my own work, but it's sort of nice in this assignment to have very short variable names. So I rename, I select, right, so I start with the data set. Sorry, I'm going a little bit too fast. In full disclosure, I recorded this video, an hour and 15-minute video just a minute ago, and when I listened back to it, there was no audio. So I'm already tired of speaking about this assignment. So, but anyway, I'll do my best to give you my best. So we start by loading the tidyverse. We load the functions for model diagnostics. We read the data set into dat_PSA. It has all these variables in it, but we don't need all of them. So we're going to select just the subset that we need. That includes the ID variable and the 4 variables we're using for analysis. And I'm renaming the variables to these shorter names. Now this, you may think that doesn't make sense. The reason I'm doing that is because I've got 4 variables that I care about, and I'm just including the one variable here, even though I'm not renaming it. It doesn't hurt to name it to the same thing, and it sort of, in my mind, okay, I haven't lost any other variables here. So anyway, it's sort of a redundant programming strategy for my own sanity. So here we've got PSA seems to range from 0 to about 21, and then there's a real big jump. We see that same pattern with volume, sort of small to 8, and then a big jump to 45. Weight goes from 10 to 48, and then jumps to 450. But age, it sort of looks symmetric here. The mean is around 65, center's around 65, going down to 40 and up to 80. So look at the scatter plot matrix now of just these 4 variables. And the reason of selecting just these 4 variables is so that we don't have the ID variable displayed as well. Let me zoom out a little bit so we can, that is probably zoomed out enough. Look at this, PSA right skewed, volume right skewed, weight right skewed. Age is basically symmetric. It's unusual for men to have issues sort of younger than 50 or 55. So this left tail is sort of that unusual group. But look at how clustered all these points are in these corners, and then it spreads out. So right away, I know that I'm going to be looking for performing a transformation on at least PSA volume and weight because of that extreme right skewness. I know that right skewness is a problem because it introduces observations that are in that far right tail. They're going to be very influential in the regression. Also, residuals are very unlikely to be normally distributed if your response variable is as skewed as this. So correlations, I'm not even going to bother to try to interpret the correlations because we don't have plots, we don't have scatter plots that are bivariate normal. Most of the correlation, the value of the correlation is going to be strongly influenced by these outlying observations in the tail. So I just don't feel comfortable interpreting the correlations. These scatter plot matrices are the same as that top row here. PSA on the y-axis, and PSA by volume, PSA by weight, PSA by age. That's these here. PSA is on the y-axis. We have volume, weight, and age. And the value to these is I've labeled the points with their ID numbers. So if we have troublemakers like this observation 32, seems like a troublemaker. All the weights are less than 150 except for this one that's 450. So it seems like there's something wrong here. Maybe it's a data entry issue, or maybe this person just is extremely unusual. If we look at observation 32, you'd think that the volume and the weight would be related to each other. But this observation 32 does not have a really large volume. It makes me think this is probably a data entry issue. Because we can't really see where 32 is. It's sort of buried in these other values. Let's see, the PSA value is really close to 0, so it should be sort of down here somewhere. Anyway, I think it's a data entry issue. So we could make a decision here. Maybe we should guess at what that value should be, or just remove it because it doesn't make sense to have a weight that is that large. Okay, moving forward. Okay, so backward selection, let's look at the full model. We're going to see right away if we fit the full model with the original variables and look at the plots. look at those residuals. They are definitely not normal. They're there's huge influence from a few observations and almost no influence from everything else. These residual plots look terrible. There's very little variance on the left and lots of variance on the right. So we've got heteroskedasticity. That means non-constant variance. Hetero meaning different, skedastic, variance. So it's same thing over here. There's a huge outlier. It looks like the Box-Cox transformation is suggesting a 0, which is a log transformation of the y variable. Yeah, so all those look terrible. So that gives us our first couple courses of action. One, we identified that this observation number 32 should be excluded because its weight and volume don't really correspond. So it's probably a data entry issue for weight. Its value for weight is 450, and other values are, the mean is 45. So maybe this was meant to be 45.34 instead of 450.34. Or maybe it was 40.34 and someone hit the 4 and the 5 together. Anyway, there's a problem here. So let's remove observation 32 because that seems to be a data entry problem. Let's also, because of all the right skewness here, take the log transform of those three variables, PSA, volume, and weight. So we'll do all that at the same time. And now we'll start using RStudio now that we're ready to make some changes. You don't really need to run that knitter code chunk. All right, so I'm scrolling down to the data, and we're going to do a couple things here. All right, so let's tag onto here a few decisions. I'm just going to work off screen just for a quick second. All right, so first thing is a filter. We're going to filter and remove an observation. Now lower down on this assignment, actually, is it here? If I page down a bit, there is a command that says remove influential observations. So I'm going to grab this piece of code and bring it up top where we're making this, where we're making that edit. Okay, so ID equals, whenever ID is in 32, we're going to remove that. Looks like I had, there we go. And I'm going to make a couple notes. Why am I removing 32? 32 seems like a data entry error for weight. Maybe 450 should be 45, for example. Okay. So I'm providing some explanation for that so that when I come back to this later, I will have a record of what my thinking was. What else do we want to do? We want to make some log variables. All right. So sometimes it makes a difference what order you put these commands in. In this case, it doesn't matter too much. All right, so let's make some log versions. We're going to work with these right here. All right, so the log version, I'm just going to call VL. I'm going to put an L suffix for each of those. Oops. Hold on a second. I copied the wrong one. Okay, that was a bit sloppy. The log variables are not age, but PSA, volume, and weight. Those are the three. Okay. Okay, good. So we've got the log version, so I'm going to append an L to each of these to mean the log version. In practice, what I would actually do these days, but I'm sort of being a bit simple here, is I'd probably name it something like this, with underscore log 2. I'm being a little bit lazy in this assignment because I'm trying to go quickly in, in this video. But anyway, so I'm going to do log base 2. And the reason I do log base 2 is because it's much easier to think about than log base 10. Log base 10 is really good if you've got like really big orders of magnitude that go from 1 to 100 to 10,000 to 100,000. We don't have jumps that are that big. We're going from, 1 to 150. And so the range of like 1 to 150, what's, 2 to the power 8 is 256. So this gives us, on the log base 2 scale, it's going to give us values from, 0 up to 7. And it gives us enough resolution. It's easy to, think about. If we got a 5, what would a 5, log 2 of 5, if you want to put that on the original scale, you raise it 2 to the 5th power. Okay, so 5, it means 32. 6 means 64, and so on. So it's sort of easy to do in your head a bit. When you see a 3 on the axis, that's an 8. So I think log base 2 is sort of a nice way to do that. There's a couple ways to code this. This is sort of the standard R syntax. You put the variable name in there, and then in the log function. If you want to be all tidyverse about it, you do log base equals 2, like that. And the reason I sort of like this tidyverse syntax here is it's easy to sort of just copy and paste it across a bunch of variables. But both syntax works just fine. Okay. I like how nicely it aligns. Okay. So there we've got the log versions of the variables. I think we're in a good place to start. Those are the two things that I wanted to make sure we did. We have to read the data set in from the beginning in order to apply all of the code that we just did. So I'm just going to click on the plus or the play button here. It'll load the tidyverse, read the data set in, and we've got a structure that includes those 3 log variables here at the end. Sorry, the highlighting was not working. This one here, and the summary includes those values. Now we also removed that extreme weight of 450, so now the max is 119. So that's pretty good. That it's still sort of a bit of right skewness, maybe. We'll find out in a moment, but not as extreme as that one data point that was definitely an outlying typo. All right, let's look at some plots. We'll make some space for the plot window and run thisggalley code, which creates the scatterplot matrix. Aha! But we have to change all our variable names. So PSA L, volume L, weight L. So anyway, this removed the observation 32, and so our weight doesn't go all the way out to 450 anymore. So this reflects one change, but this is the best change. Look at that beautiful symmetry on these 3 variables that were super right skewed. This is awesome. Look at this powerful correlation between PSA and volume. That is awesome. Slight positive relationship between PSA and weight. With age, it doesn't look like there's much relationship. Looks like there's a small positive relationship between weight and volume. I guess I would expect that to be true if I'm remembering the meanings of those 2 variables correctly. If I scroll up to the top, the cancer volume and the prostate weight. So I'm interpreting this as the weight of the cancer is somehow distinct from the prostate. Maybe it's growing on top of the prostate, and so you can measure the weight of the prostate separate from the volume of the cancer. But it could make sense to me that if you have a larger prostate, that maybe there's more opportunity for cancer to grow or something. I admit to being quite ignorant about this topic. Anyway, let's just be so happy about all this symmetry here. We have this tiny bit of left skewness on the age. It's a bit like it's symmetric, and then there are a few outliers on the left. It's unusual for people in their 40s to have issues with their prostate. So that's that left tail there. Now I'm quite happy to interpret correlations. We've got between PSA and volume a correlation of 0.6, which is rather strong, significantly different from 0. Between PSA and weight, not a significant correlation. And between volume and weight, not a significant... Oh, hold on a second. I did it again. I need to change my variable names. PSA log, log, log. Okay. Let's run this again. Aha, much better, much stronger. Okay, so 0.7, significantly different from 0. So this top table is the correlations. The bottom table are the p-values testing whether the correlation is different from 0. Between PSA and weight, significantly different from 0. I got concerned because I was looking at this plot and knowing that this correlation should be much stronger than it was in that previous table. So that tipped me off that I needed the L's on my variable names. Between age and PSA, at least at a 0.05 level, not significant, but weight and volume seem to be correlated here. This is not really strong enough to worry too much about. In later chapters, later on in this course, we will be thinking about what to do when our predictor variables are correlated, because it does cause problems with model fitting and with hypothesis testing. I have this additional plot here. Oh, but I'm going to have to change all the variable names to the log version. Okay. So this is a point, as I'm sort of typing this in here. This is a point where it may have been handy, because we have all the code written on the original variable names, to not create new variables, but to overwrite the existing variables so that all the code would work on the on the log scale without actually renaming the variables. That is a choice that you would make, as long as you're very careful about keeping track of what scale your variables are on. That's a direction you could go in this assignment. You could do a mutate, right? So what you would do is, in this mutate statement, you would make this left-hand side just be PSA, and where PSA is the log. And so you're assigning the log version to the variable PSA without the L on there. And then all the code just works, but everything's on the log scale. That's probably something I would consider doing myself. Though I don't mind doing some additional typing if there's a big benefit in clarity. And I think adding the L makes things clearer. I know what scale I'm on. All right, let's go. Why don't we just knit this and make sure we're reviewing all the steps here. You know what? We can do a few more things before we review the results. Let's fit this full model with the log version, and look at those residual plots on the log scale. All right, we will open this file in the browser, and once RStudio finishes compiling the most recent version, we will refresh this window. Okay. All right, so let's scroll down and make sure we're answering all the questions. So look at the data, describe the patterns you see, ranges, unusual observations, nonlinear trends. Okay. So in terms of ranges, it's hard for a non-expert to really have a sense of what the appropriate ranges are for PSA volume and weight. So I'm not thinking too hard about those. Ages totally seem appropriate for this. In terms of the patterns, you'd want to talk a little bit about what we saw initially about the right skewness and that outlying observation for weight, and how we address that. And then Now we've got positive correlations between log PSA with log volume and log weight, and a slight positive correlation between log weight and log volume. Otherwise, no real correlations with age, and no real outliers that we can see from the scatterplot matrix. All right, we already discussed the interpretations of these correlations here. You know what? I take this back. Looks like weight and age are correlated as well as volume. So those volumes and weights, at least log volume and log weight, tend to increase with age. Let me just page up for a moment. Volume and weight, so there's a slight positive relationship here, slight positive relationship here. I can see that. Okay. I guess that also makes sense with what I understand about the prostate and older men having trouble peeing and so on because their prostate gets too large. So that makes sense to me. All right. And so that would, you'd basically type all that stuff here under that solution for this section. All right. Let's look at doing backward selection by starting with the full model and interpreting those regression diagnostic plots. So here is the linear model on the log scale. Looks from the face of it, we've got residuals that are roughly symmetric in the 5-number summary. So that's hopeful. As we'll see in a moment whether normality is met. It looks also like log volume and log weight are going to be important, but maybe not age. And we're explaining about 60% of the variability in PSA, which is pretty good. So it's a nice place to start for a model like this. We have these residuals already look really good. In terms of influential observations, it looks like 37, 94, and 68 is not really that much. So let's keep our eye out on 37 and 94. Now, these are the observation numbers for the linear model. That's not the ID number or the row number in the original data set. We removed observation, I forget now what the number was. You're all yelling at me. 32. Okay, so we removed observation 32. If you remove observation 32, all the higher numbered observations decrease by 1. Okay, so let me page down again for a second. So that means what is appearing as 37 here is actually observation 38. And observation 94 is ID 95. All right. We started with 97 observations, and if you can count these lines here, after 94 there's only 2 more, which is 96. So all of this makes sense. If we need to remove these observations, we'll need to remove it by the ID that's 1 greater than each of those 2 numbers. Okay, why are 37 and 94 influential? Is it because they have high leverage? Here's 37, and here's 94. And so they have a bit more leverage than most of the data points, but they're not super high leverage. So we'll just continue to keep our eyes out for those in these plots. All of these residual plots look beautiful. There's no structure, there's no increasing variance, there's no curved pattern, so this looks great. 94 sort of has a high residual here. In the added variable plots, even after adjusting for the other variables, there's still a relationship between log volume and log PSA. Okay, so volume is an important contributor here. After adjusting for the other variables, weight and PSA seems to have a positive relationship. But after you adjust for the other variables, age doesn't seem to have any relationship. So we'd probably expect after model selection that age is going to be removed. Let's look at some of the variable observations that we know about from influence above. 94 seems to be a high outlier here, and it's sort of a pulling up on this regression line. That's what makes that influential. Over here also it has a large residual, so it's sort of pulling up on the mean here. And 94 here is also sort of pulling up a little bit on and changing the slope of that regression line. So I can see why that observation is being influential. 37 mostly just appears here, I think, and it's the one with the lowest weight. And so this is pulling up on this regression line. It's actually sort of counteracting the stronger positive slope that it otherwise would have. So in a way, this isn't exaggerating the model. It's actually, bringing it down a little bit by making this slope less strong than it could be without it. All right. So I feel pretty good with this. I would maybe not worry too much about these two. What we will do after we do model selection is we'll remove these two observations and see what influence they have on the model. And if they don't really change our inference, we'll leave them in because we don't have a good reason to exclude them otherwise. All right, address model fit. So go ahead and read this, but basically the things are looking pretty good. I think it's time to do backward selection. So what we would do here now, model selection starts here, so it's time to write some code. Okay, so if you go to a previous assignment, you can grab the code for the model selection, and it will look like this. All right, so this is the same code that you've seen in the lecture notes and in the assignment 5, class 5. We're going to do stepwise regression. We're going to start with our full model, which, recall, is what, if I page up here, is what the linear model object was with the full model. So we're going to start at that model. The direction of our stepwise regression is backwards. We're going to include the f-tests and p-values in there to provide us a little more interpretation of why it's making its decision. And the main thing here is, I believe at some point, if I page up for a moment, I say fit the appropriate full model in backward selection using BIC, the Bayesian Information Criterion. So if I page back down, if for BIC, I say in this comment, for BIC, include k equals the log of the number of rows of your data frame. And so that's what this is, the log. This log, by the way, is the natural log, base E, the number of rows of the data set. So that is the appropriate BIC penalty. So now I'm going to run this. Oh, rats. Let's see if, so it didn't like that. It must, let's see, did I make a, so LM PSA full, LM PSA full. Oh, maybe I didn't run these before. I think we were just looking at them in the on the original. No, I don't know. I don't know why that didn't work. Anyway, it's working now. I must not have run that code before. Okay, let's look at the output of the model selection. We started with an AIC of 28, and this is our full model. It had volume, weight, and age. And this is telling us that the first column is telling us what decision to make. So, for example, and this is sorted by AIC. This AIC value, by the way, is actually BIC because it's whatever the information criterion is with the penalty that you specified. BIC is very similar to AIC for model selection. When you have larger sample sizes, BIC tends to select smaller models, meaning having fewer predictor variables. So it's a way to get a more parsimonious model by having fewer predictors. Okay, so recall we want to minimize the AIC, or BIC value in this case. And so we want this to be as small as possible. This AIC column is sorted by AIC. And so we can go from, by doing nothing, we start with this this is the BIC that we have at this moment. If we remove age, which is the recommendation here, we will go from 28 to 24. And the significance of age in the model has a p-value of 0.28. So it doesn't seem to be that important. We can remove it, and when we do, we go to the step 2. So it has only these two variables. It's suggested that we do nothing. If we were to remove weight, the AIC would go up about 8 points, and if we were to remove volume, it would go way up. So we definitely don't want to remove volume, and we don't want to remove weight as well. So I think we found a model that we like. We called the resulting model from the BIC model selection reduced BIC, and what I typically do is I then create a new linear model object which is called final, and I'm going to use that in all the resulting analyses. So what more do we need to do? Let's look at a summary of the final model. And let's also, if I page up for a moment, find the diagnostic plots and make those plots for the final model. I'm going to clear my plot area and create and make those plots. All right, so let's look at the summary of the final model. After removing age, we're still explaining over 59% of the variability, which is really great. These two variables are highly significant in the model. And if we take a look at the residual plots, the QQ plot tells us that our data, our residuals are nice and normal. 37 and 94 are still important, though 68 has become sort of more influential than 94, and it's because 37 and 68 are both have high leverage. So we'll keep our eyes out on those. These residual plots still look really great. We don't have one for age anymore because age is not in the model. Here's 68. It's sort of working against us. It's sort of trying to leverage this regression line to be less sloped. So, and same thing with 37. So even though these are influential, they're sort of influential in a conservative way, and not making these slopes more extreme than they otherwise would be. So I feel quite good with those, with these, with the diagnostics here for this reduced model. Let's knit this and run through the assignment and make sure we're not missing anything. It's hard to do too much thinking in this editor window because, you know, there's just limited space on the screen. If you've got a larger monitor at home than this tiny space, which is only a quarter of the size of my monitor, you will certainly be able to make better decisions in that editor window. All right, I'll refresh this assignment. I'll start from the top, scroll down, and skip over a bunch of this stuff. All right, here's the backward selection. This is the output and the plots for the full model, and we're happy with this. Here we've done backward selection, and we dropped age to get the final model, and here's the result of the final model. We're basically happy with this. Okay, let me page up now for a moment and look at the description of this question. Okay, fit an appropriate full model and perform backward selection using BIC. Discuss the diagnostics in terms of influential observations or problematic structure in the residuals. We saw that the residuals look great. The couple influential observations seem to be reducing the slopes in the model, so I don't see very much problem there. In a little while, we're going to remove those two observations and see whether there's whether they're influential or not. But so far this looks really good. All right, so those are the types of things that I would say after all this output. I would write some discussion here about what you did. All right, if the model doesn't fit well, then address the model lack of fit. So we've done all of this previously, and you need to document somewhere in a reasonable place the choices that you made. So go ahead and read all this. Maybe a good place to, I mean, there is a solution here. Maybe this is probably the best place to document the decisions you made for addressing model fit. So down here I would say, you removed observation 32 because it seemed like it was a typo in the data for weight. We did the log transform, etc., etc. So sort of like make maybe just a numeric list or something here that discusses each step that you took and why you made each decision. All right, this actually probably is a good point to see what happens if we remove these, say, 2 or 3 most influential observations. So let's give that a try, and then and we'll make some comparison. Basically, the main things we want to know is, do our slope parameters, our model coefficients, change very much when you exclude the most influential observations? So I'm going to find a way to have both sets of results. Oh, I know how to have both sets of results. Okay, so I'm going to use this web page right here, which I won't refresh, to have the coefficients when these observations are in the model. I'll go over to R, and I'll scroll up to the top where I did the filter. Here we go. And I'm going to include a couple other observations. I need to remember which ones. So remember, I have to add 1 to 37, and I don't know, should we just do these 3? 94 is not that different. 68. Like I said, I don't feel too bad about these, but let's just sort of check on them. So 38, 69, and 95. Okay, so we'll remove those observations and we'll knit the document. That will produce output in this window. Let's see if I can get this window more to fit in here. Okay, looks like it just finished. And I'll scroll down and we'll take a look at what has happened. Look at the Cook's distance. See how horizontal they are? This is with the full model, I believe. Yep, the full model. So no real influential observations anymore. Everything still looks great in terms of the residual plots. 92 has a large residual, but doesn't really seem to be a troublemaker. Backward selection removes age, but keeps the other 2. We look at our final model. We have 2 points up here which are slightly more influential than others, but this doesn't seem to be problematic to me. Everything else looks really good. We are explaining slightly more variability in the model, and if we put up the fit with, so on the left we have the summary table with those 3 influential observations. On the right we have it without. So we can start to compare these numbers. So in terms of coefficients, we have 65 and 66, and over here we've got 65 and 72. They're both positive. They're both, about 2/3. They're sort of about the same. The R-squared value of 59 versus 61 or 62, that's also about the same. So really no difference in inference by removing those observations with high Cook's distance. So I'm thinking that we should just keep them in and move to the end. All right, let's continue down. So I refreshed this page, so this now has, let's undo that, right? I'm going to keep these in. Okay, so I would make a comment down in the section where you're addressing model fit that you removed, those certain observations to assess how sensitive the model results are for those influential observations. You saw that they didn't change by very much, and therefore you decided to keep those variables or those observations in the model. All right, so we're in pretty good shape now. F5. All right, let's do the last few parts. All right. Okay, predictive ability of the model. That is the multiple R-squared value. What proportion of variation in the response does the model explain over the mean of the response? Okay, so I'll page up a little bit. That is the output for the final model, the multiple R-squared. So this is not the adjusted R-squared, which is used for model selection, and we will discuss that quantity later. It's just the multiple R-squared. So it's about 59%. This is quite good. So now I'm going to spend some time. Let me sort of, okay. There's always a dozen ways to do something, and I always struggle to know which is the best order. Let's do one thing at a time. So let's go over to R and start doing some writing. So I'm going to jump to the bottom, then page up. There's the predictive ability of the model, where I'm going to write the solution. Now, we know from this summary that there's this value, multiple R-squared, that's being plotted. Therefore, there's some way to get to that value. If we ask for the names of the objects within the summary, we get this list, and there's a variable called R-squared. And we can get to that value by, from the summary, putting a $sign and doing R dot squared. And that is this value right here. So I can use this to print the actual value in the output. And we've seen this last semester, and what you do is a single back tick, which is the key above your tab key on the top left corner of your screen. Put the letter R, because I want this command to be interpreted by the R language. So if I highlight that and press Control Enter, or Command Enter if you're on a Mac, it will submit it down to the console and print it out. I think having 7 decimal places is a bit extreme, so I'm going to reduce this to, I'm going to pass that value to the signif function and only get 3 significant digits. So I think that's a good summary there. And so now I just need to write a sentence that includes that number. So I will say something like, the model explains R-squared equals that amount of the variation in the response, PSA-L. And you can write a little bit more if you like. I'm going to take a moment and I'll knit this so we can see that this actually puts the value where it should. But then let's tidy up this equation so it looks beautiful. And we can do that by using LaTeX, or at least LaTeX syntax for producing this equation. So here's what we just did. The model explains R2 equals 0.594 of the variation in log PSA. So let's make this a nice equation. First thing you can do is wrap this in $signs. In LaTeX, let's see, I should show you something. How about LaTeX equations? So I really like this Wikibooks of LaTeX, and this is bringing us right to the mathematics section. To typeset equations in LaTeX, and by the way, this is not a class in LaTeX, and I'm not really advocating for this, but some of you are going to want to know how to make beautiful equations, and so here's a 30-second way of getting it. The text shorthand for getting equations inline, an inline equation, inside of a sentence, is just to put single dollar signs around the equation. If you want to display equation where it's it's on its own line and centered, then you put double dollar signs. Okay. So there's a suggestion that you should avoid the double dollar sign notation. I actually never use that in my own work. I use other ways of doing equations. But there's ways of doing Greek letters. So all these commands on the left render these nice symbols on the right. There's nice operations like this: cosine theta, cosine squared. You produce this equation on the far right. You can do limits, you can do summations, all sorts of things. So this is a fantastic way to typeset beautiful equations. And the syntax is quite straightforward once you learn it. There's a learning curve, of course, and it will take a little while if you decide to start doing this to make beautiful equations. But let me at least show you how to do that for this one. So r squared is r caret 2, to put the 2 in the exponent. You can see that it gives you a display here of what it would render as. Now, of course, this number, it's trying to typeset this whole thing in LaTeX, but it obviously this is not LaTeX. It renders a number. Anyway, so this is going to give us a nice r squared. Let me just knit this part. The next part is the PSA part. So we want log 2 of PSA. Okay, so this will do pretty well right here. In fact, let me just knit this one more time so we look at the output. I'm going to show you in a second how we can improve this, and then we'll go on to the next part of the assignment where we interpret the regression coefficients. All right, so we'll go over to here, refresh the page. Here, okay, nice. R squared of the variation in response log 2 PSA. Now, the thing I don't like about this, but you will see this, people typeset this way all the time, is that I think of italicized or emphasized or slanted text as being variable names. So this is like variable L, variable O, variable G, PSA as also as all variables. So we really want these words to stand up. So the way to do that, so log is a special command in LaTeX, and so if you do a backslash, it will treat it. You can see the display change here from all slash L's or slanted L's to upright log. And then for any other text, you can wrap that in a command called text rm, which means typeset that in Roman font. Roman font is just letters that we use, and it doesn't make them slanted. So anyway, this I think is what we want the equation to look like, log 2 PSA. All right, let's knit that and move on to the next part. We've answered that question. Interpret the final model. So we're going to spend a little bit of time here because we've got a few equations to write. The first thing is we want to write, okay, here we go. Isn't that nice? All right, that's some proper, oh, it does look a little bit weird here in terms of the text size, but I think it's just this RStudio displayer. If we go over to the browser and refresh, it still looks a little bigger than the normal text. I don't know. I still prefer seeing beautiful equations. All right. So first write the model equation and then interpret each model coefficient. So those are the two parts here. So the model equation, so I'll say the final model is, let me page up for a second. I'm going to steal the equation from here, from the full model. Well, yeah, that's fine. And page back down. The final model is and I have to remove age. Okay, so I've got an equal sign here. I'm going to put each of these on its own line because that will be handy in a moment. I also have an intercept that I need to worry about. Okay, so I've got sort of an intercept. Okay, and then I've got the values of the coefficients. So if I go back to the console window in the bottom and look at the summary table, it's this coefficients table that has these estimates. Okay, so if I again look at the names of this summary object, I have an object called coefficients. So that means I should be able to put a $sign coefficients and get that table. Awesome. This is a table, so you can index the values in this table by rows and columns with square brackets. So if I go to the first row and first column, I should get that first value. If I look at the second row and first column, I get that second value. So now I can pull out any value here. I'll make one side comment here. There is a sort of a quicker way to get coefficients with COEF, which just gives you those three values, and then you can specify, like the second one here is the one for volume, 0.65. So this is sort of a quicker way to get to the coefficients, but I always use this way because in my own work, I'm very likely interested also in the p-values or the t-statistics or something. And so indexing by elements of this table I find to be more useful for my own work. So anyway, we've got the code here for these values, so I'm just going to copy that. This first one, 1, is the intercept, so I'm going to put that right here. I'm going to wrap it with a tick, R space, and the value, and right away I'm also going to print 3 significant digits. Let's highlight just the code part and submit that, and that is the output that I'm going to get. Maybe 4 is better. Doesn't matter that much. Okay, let's put the other coefficients in there. So we've got that one times the volume and that one times the weight, and we've got the second row and the third row. And that's the model. Okay, let's knit this and see what we got, and then we'll spend another minute and I'll show you how to make this beautiful. Now, once we've got something that works, and we're going to see that it works in just a second, it's worth copying that text so that if you mess something up as you're making it better, which I do all the time, then you've at least got sort of that old version that you can go back to. All right, so here's the final model. This is the text that we just put in. It's got those values in there, and I realize I think I probably like 3 significant digits better than 4. So we're gonna make this better. So we'll reduce this to 3 in our improved version. All right, so PSA is actually the log 2 of PSA, and we already put that code up here. So I'm going to copy that from up there and bring it down here. That's actually our response variable. I'm also going to typeset this as a display equation by wrapping it in a double $sign. The last part here is for the volume and the weight. So I'm going to copy and paste the text for the PSA, and instead of PSA, this is the volume, and instead of PSA, this is the weight. All right. I think, did I just do something weird? I didn't mean to. Oh, I see. I edited the my first version of this instead of the second version. Anyway, it'll be just fine. Let's take a look and see that it's good. If we're happy with this equation, then we'll go on to the next part, which is to interpret the model coefficients. All right, so that's done. We'll refresh the HTML look at that. Log 2 PSA equals the intercept plus the slope of log 2 for the volume plus log 2 of the weight. I like it. So much nicer than this thing. Both are totally fine for my class. I don't care about things being beautiful. I do care about you understanding it and about doing your best to have it be correct. All right, so there is that. Write the equation for the final model and interpret each model coefficient. Now, what's the generic interpretation of a beta coefficient? It is, so the model predicts that with all other predictors held constant, that the response variable, we'll fill in the actual things later on, that the response variable is expected to increase, beta units for each unit increase in the x variable. Okay, so I just sort of dumped the generic language there, and now I'm going to fill in what we care about. So the response variable is expected to, so I've got two variables here. Why don't we do a little list. Okay, increase for the first variable, that's this number up here. And there's the volume. Okay, increase that number value, units for each unit increase in the log of the volume. We've got to wrap this in dollar signs since it's an equation. Okay, so the response variable, I've probably should specify what that is. Log 2 of the PSA. Wrap that in dollar signs since it's an equation. Okay, I realize I'm moving a little fast. Let me slow down just a little bit. The model predicts that with all other predictor variables held constant, that the response variable, log 2 of PSA, is expected to increase by, if we highlight and run that command, we get 0.653 units for each unit increase in the log 2 of the volume. Now I'm confident, so I'm going to copy this and also do this for the variable 3, which is the log of the weight, and knit this so we can see what this looks like. Then we're going to improve this a little bit further. Now, if you don't do all this copying, all this fancy text stuff, I don't care. You can hand type these numbers. That's totally fine also. Okay, but let's see what we've done. The model predicts that with all other predictor variables held constant, that the response variable, log PSA, is expected to increase by 0.653 units for each unit increase in the log 2 of the volume. Perfect. And it will increase by this much for each increase in weight. Now the last part here, which is most valuable to those of you who need to keep track of units, is that when we've got units here, we can fill that in with what the actual units are. So let's page up to the very top to the table where I've got the description of the variables. The PSA level is in those units. Is that nanograms per milliliter? So I'm going to copy that text and I'm going to go over to RStudio, and whenever I've got the response variable is expected to increase by that many units, I'm going to put those units in there. Now the only thing I need to change here is that those aren't the units that are really going to change. It's going to change by the log 2 of those units. So let's make sure that we've got log 2. Oops. Okay, log 2 of, and the stuff that's in here I'm going to wrap with text rm so that the ngml are not slanted. Okay, and it gave us a preview here, log 2 of ng per ml units. So this is nice. That's what we want for our response units. I'm going to make that here too, so I hope you're following along. You know, sometimes it's nice to put in some line returns so it's a little bit easier to see. Okay, for each unit increase, so what are the units of our volumes and weights? So I'll go back to over here. For the volumes, it's cc, but it's going to actually be log 2 of that. And the units for weight is grams. Okay, so now I'm going to make those into the log 2. So I'm just going to sort of copy all this stuff, put it here, and instead of ng per ml, we've got cc. And for, let's see what we got. And instead of cc, we've got gm here. All right. All right. I'm going to knit this. This is going to be beautiful. You guys are convinced of this, I hope. All right, we'll refresh this over here, jump to the bottom. All right, the model predicts that with all of the predictors held constant, that the response variable log 2 PSA is expected to increase 0.63 log units for each log unit increase in log 2 of volume. Awesome. And same thing for the grams of weight. That's what you'd want to see in a journal article. That's my opinion about that. All right. Last step is about inference to whom. So who does this make? So I'm not going to type this out, but the inference is to the people who appeared in the study. So if we page up to the top, and I think I made a comment about this at the very beginning, these men, so it's men, right? So this model applies to men who are, in terms of their ages, who are 40 to 80 years old, who were about to undergo radical prostatectomies. That's basically it. I don't think this really applies to the general population of men. It doesn't apply to young men, and these really applies to fairly extreme cases, because they were going to have surgeries to remove their prostate. So that's what I would say for inference to whom. Okay. We did remove an observation early on because it had a very large weight. Now you could make the argument that maybe that wasn't a typo, and maybe if it really was 450, you might then say that this applies to people whose prostate weights, or hold on a second, whose prostate weights were less than 120, something like that, so that it's sort of restricted to that range of weights. So that would be my last comment. The last thing we'll do, I promise, is to look at the 3D plot. So we've got here this 3D plot just to check it out. Like, what happens if we're lucky, in a way, that we have a model that only has two predictor variables and a response, because then we can, let's see, summary. I just want to get the model equation. Here we go. Because with 3 variables, we can look at a 3D plot. Okay, let's make this as big as we can. Oops. While going into the display section. Okay, that's pretty good. Okay, so PSA is on the vertical axis here. Weight is coming at us in cyan, and volume is there in magenta, and it's the log version of all 3 variables. We have nice scatter above and below the regression surface, and what I'm going to do is I'm just going to rotate the surface and look for any unusual patterns in the residuals as we rotate. And because the residual plots only show us residual patterns with respect to one variable at a time. But this way we're sort of getting a multivariate look at those residuals, and I don't see any real unusual structure of those residuals. There's no like curvature over and under or anything like that. This looks fantastic. So I'm really super happy with this model for this data. We came a long way from where we started with those super right skewed distributions to something that really fits well. So I'm super happy. This is in my opinion, a fun example data set to practice all the skills that we've developed so far. So I hope that you've had a good time with it too, and I'll see you in the next one.